Okay, hello. This is the second video out of 4, and we're going to work on activity 10-1, estimating SS sum of squares in analysis of variance. So basically, I took a bunch of screenshots of the sections of the worksheets, and just as in the class, we'll go over these problems, and feel free to take notes and write down the stuff in the video, and kind of just the same way that we as we do these activities in classroom. Okay, so here's the data set. You already saw that. It's a replication of the Strayer and Johnson 2001 experiment in which they examined the effects of having a phone conversation on driving performance. So it's a hypothetical data set, and we had a total of 15 participants, 5 for each condition. And condition 1 is no phone, condition 2 is handheld, condition 3 is hand-free. And these are the performance measurements. The mean for each condition, 4, 1, 1, and the grand mean is 2. So that is the data set that we are going to use. It's a very simplified, but we can use that as an example to demonstrate how to estimate the sum of squares. And the important thing, of course, is not only to just kind of know how to estimate those sum of squares, but understand for each part what exactly we are calculating. That's always the point. It's the point of going through these activities is not just crunch the numbers, but to think about the reasons that we are crunching those numbers. Okay, so this is the first part. Has nothing to do with the numbers, but it's kind of an idea about what is responsible. What are the reasons that contribute to, what are the things that contribute to the between group variation and within group variation, right? So the first part is about the difference performance between the conditions. In other words, between group variance. And then the second question has something to do with what are the reasons that might explain for difference in performance within the same conditions. Now, the difference between these two, obviously, is that if they're within the same condition, then any reason that you come up with cannot include treatment because it's within group. Everybody receives the exact same performance. So anything that specific reason you come up with over here, it has to be random, non-systematic reasons. So we call them errors in experimental research. And but if we're talking about performance between the conditions, then in addition to errors, there's one crucial possible reason is that they were in different treatment conditions. So essentially, the treatment effect, that's systematic effect. Okay, so there's no particular correct or incorrect reasons, and just think of anything that you can think of that might affect their performance. Okay, so but for the between condition, for the between group variation, one of the reasons obviously is the treatment. Okay, so that's the first part you need to do, and then we're going to crunch the numbers. So we're going to have these numbers on top, and so we can look at these numbers when we do the calculation. Again, just refresh your memory about those. That's the sample mean, and that's mu of t, which is the grand mean. We might as well say this is M1, this is M2, and this is M3. Okay, so these are the sample means. Okay, so the first thing that we are going to estimate is the total sum of squares, because conceptually this is the most straightforward. So how do we estimate sum of squares? Well, this is the basic equation. Sum of squares by definition equals x minus m squared, and then we add them together. So if we are talking about sum of squares total, then the x actually refers to all 15 participants. Okay, so all 15, each and every one of them. And the m Since we're talking about the total sum of squares, we're going to use the grand mean. Okay, so here's a bit of notation, explanation of a notation we're going to use. We're going to use x to indicate the measurement, and we're going to use two subscripts, I and j. So x of I and j. I refers to participants. Okay, so the number of participants. And j refers to condition. So when we say x of I and j, we're talking about the ith subject in the jth condition. So for example, participant is subject number 1. In condition 1, we are going to name that participant as x of 1, 1. So the first number represent, this is a participant number 1. The second number is the condition 1. So x11 equals 4. Second participant, x2, 1 equals 3. All right, so this is a second subject in condition 1. That's 3. And what about this participant? Well, that's subject number 1, but in condition 2. And what about this one? This is subject number 1 in condition 3. Okay, so the second number always indicates the condition number. What about this participant? This is subject number 5 in condition 3. So that's x, 5, and 3. So that's kind of just a notation that we're going to use when we deal with multiple participants and multiple conditions. Just kind of make it easier for us to keep track of the things that we try to do. Okay, so first let's estimate the total variations in the driving performance. And the basic equation we're going to use is this. And then we have xij. So the equation we start with, SST, sum of squares total, equals. So if you compare this equation, we essentially have x minus m, right? X minus m squared. But what makes this a little more complicated is that we want to do this for all participants. So x of I and j, all the conditions. So total of 15. And for each of these data points, we're going to subtract the grand mean. So that will give us the estimate of total sum of squares. Okay, so one thing that you can do is to just finish the naming of these data sets, of these data points. So for example, this is x31, x41, x51, x12, x22, x32, x42, x52, and etc. So kind of you need to get used to this kind of notation, subscripts that we use to indicate which subject we're talking about. Okay, so that is the basic equation, and then we just expand this equation. So we start from x11. So that's subject number 1 in condition 1, minus the grand mean, take the square. Second subject 2, 1. That's 3. That's minus the grand mean, squared, etc. So finish all 5. And then we move on to the first participant in condition number 2. So that's x12 minus mt squared, etc., etc. We finish all 5. And then the 5 participants in condition number 3. So x13 minus m of t squared plus, etc., etc. Last participant, x5 of 3. The fifth subject in condition 3 minus the grand mean, take the square. Okay, so we basically expand this equation, and you should have all 15 of them. And then you just plug in the number. So that's 4 minus 2 squared plus 3 minus 2 squared, 0 minus 2 squared, 1 minus 2 squared, and 0 minus 2 squared. Okay, so I just omitted lots of those, but when you work on the problem, make sure that you have all 15. It's really important to actually do the calculation. Okay, so if you do everything correctly, the result that you get should equal 46. Now, if you get a different number, you made a mistake. I have double-checked this number many times, so I know this is correct. The total sum of squares equals 46. Okay, so again, let's kind of take a moment to think about how we estimated sum of squares total. This is combined all 15 participants, and we take the value and we compare that with the grand mean. Okay, so that's SST, or sum of squares total. T stands for total. Next slide. So exact same equation, but this time we are going to estimate the variations between the conditions, between group variation, between treatment variation. And if you recall from our discussion in the previous video, this the source for SSB includes both the treatment effect and also random error. Okay, so let's start to do that. Now, we'll use the basic same equation, but this time, because we are going to estimate between group variations, between conditions. So essentially, we are going to compare each one of these sample means with the grand mean. Okay, so it's still x minus m, but the x is actually sample mean. And the m, the mean, is going to be grand mean. So we're going to compare each one of these means with the grand mean. And that will give us the estimate of how much variation is there between these different conditions. Okay, so here is the equation. M of j. Remember, the two subscripts, I refers to subject, j refers to the condition. So essentially, when we say mj minus mt, we are saying m1 minus mt, and then m2 minus mt, and m3 minus mt. Okay, so j equals 1, 2, 3. We have a total of 3 conditions. And why do we have to multiply by the n of j, which is the number of subjects in each condition? Here's the reason. When we compare the mean, the average, with the grand mean, we are doing that for each and every participant in that condition. So since there were 5 participants in this condition, we have to do that 5 times. Okay, so that's why it's 4 minus 2. So m1 minus grand mean is 2. That's squared times 5. So once for each participant. Same thing for condition number 2. So 5 times 1 minus 2 squared plus 5 times, because we have 5 subjects here, 1 minus 2 squared. Okay? And so this is actually exhausted all 15, because that's 5, and that's 5. So if you do this correctly, SSB should equal 30. So between group variation, sum of squares, B between equals 30. So so if we go think about what we discussed previously, what are the things that contributed to this between group variation, SSB? Well, the answer is treatment plus random error. Okay, so that's the second part of the sum of squares. Now we have one more left, which is SSW, sum of squares within groups. So how much variation is there within group 1, within group 2, within group 3? We're going to use essentially the same equation, but in this case, x refers to these actual data points. So x of I and j. Now, what is m? What does it mean? What do we compare these numbers to? Well, we are looking at within group variation, so we have to compare each and every one of these data points with its own group mean. So x of ij minus m of j. So m of j refers to the mean for each condition, right? M1, M2, and M3. Okay, so I just added another sigma to indicate that within each group, we have to add across the 5 participants. And then the second sigma means that we add across 3 conditions. Okay, so it equals sigma xi of 1, group 1, minus m1 squared plus sigma I of 2 minus m of 2 squared plus sigma x of I of 3 minus m of 3 take the square. So this is how much variation, how much sum of squares between within the group 1. And this part is group 2. And this is sum of squares for condition number 3. Since we're talking about the variation within conditions in this entire experiment, we have to add them together. Okay, so first one, 4 minus 4 squared. And the last one is also 4 minus 4 squared. So within this parenthesis, I used a square parenthesis. So this is how much variation is there within group 1. And this is how much variation is there is between within group 2. And this is group 3. Now, when you complete this part of the worksheet, you should complete all 15. So instead of just ... you should have 3 minus 4 squared, 6 minus 4 squared, 3 minus 4 squared, and that is the condition number 1. And you do the same for condition number 2 and condition number 3. Okay, so once you add all of these together, you should get 16. This is within group sum of squares. So what are the reasons that we have this within group variation, within group sum of squares? Random error, right? So between subjects, between condition, between group variation, sum of squares. The reason is treatment plus error. But sum of squares within groups. The only reason we are looking at these different variations, sum of squares, is because of random errors. Okay, so now we have finished estimating the 3 sum of squares, SST, SSB, and SSW. This is just a summary of the equations that we just used, SST, SSB, and SSW. So if here we have only one sigma. If you want, you can add another sigma. This part is the degree of freedom. So for each sum of squares, we have a corresponding degree of freedom. So the capital N refers to the total number of subjects. So 5 plus 5 plus 5, N equals 15. So we have a total of 15 subjects. So the total of degree of freedom equals 15 minus 1 equals 14. So we have a total of 14 degrees of freedom. How many degrees of freedom do we have between groups? Well, that equals k minus 1. K is the number of conditions, how many different groups we have. In this case, we have 3. So k equals 3. 3 minus 1 equals 2. So we have 2 degrees of freedom for between group sum of squares. And how many degrees of freedom do we have for within group? Well, that equals the total number of subjects, 15, minus the number of conditions. That equals 12. And according to our calculation, SST equals 46. SSB equals 30. And SSW equals 16. Now you notice something interesting. If we add SSB and SSW together, 30 plus 15 plus 16 equals 46. And if we take the degree of freedom for within 12 plus degree of freedom for between, it equals degree of freedom total. 12 plus 2 equals 14. And that is not a coincidence. That is actually a very important thing to remember about analysis of variance. It's the concept, it's the idea of partitioning the variance. The total variability, sum of squares total, is divided into between group variance. Measures differences occurred because caused by systematic treatment effects, random unexpected factors, error, and within treatment variance, this part is caused only by random unsystematic factors, which is error. Okay, so in another word, SST, total sum of squares, is partitioned into SSB and SSW. Likewise, the degree of freedom total is partitioned into degree of freedom between and degree of freedom within. So, for one-way between subjects analysis of variance, okay, between groups analysis variance, the partition of variance refers to the fact that SST equals SSB plus SSW. So, in our example, 46 equals 30 plus 16. It's very neat. Its total variation can be divided into those two parts. One is caused by error itself, and the other one is caused by error and treatment. Okay, so that's the partitioning of the variance. And this is pretty much the end of activity number 1. So once you're done, finish this part, the usual thing, take a picture and get it submitted. This time, the due date for the activities is actually Sunday, this coming Sunday, March 30th. But I hope that you will finish this earlier during the week, if possible by Tuesday, and then activity 2, activity 3 by Thursday. If you can maintain that schedule, it would be great. So don't wait until the last minute to try to do everything. That's just not a good idea. Okay, so this is the end of the second video. In the next video, we'll go over the activity 10-2. We're actually going to conduct and finish the omnibus F test.